Hello, everybody. I'm Dimitri Roditchev, and today I will discuss a little bit superconductivity in single atomic layers of lead on silicon. So this is a result of a collective work in my group in Paris, but also external collaborators, and specifically for the talk, the main input is due to Juan Carlos Cuevas from Madrid, theoretical, and Milorad Milosevic, and collaborator from Antwerpen, and also very much help from Michael Tringides and Sergei Boshko, who are specialists in surface science physics. So we do STM, scanning tunneling spectroscopy, right in the center of Paris, so somewhere in between Notre Dame de Paris, Jardin de Luxembourg, and Gare d'Austerlitz. So if you are in Paris, you can easily find us. The difficulty, as you understand, is that we have here in the vicinity 4 metro lines, so it's not so easy to do. Our team is Quest, it's Quantum Electron Spectroscopy team, and I would like to advertise you about some activities that I cannot cover today. One is we're interested not only in vortex physics, but also in interactions between magnetism and superconductivity on atomic level. So, for instance, here, recent paper that appeared in Nature Physics recently, we studied individual impurity of iron embedded in niobium diselenide, which is a two-dimensional superconductor. And the interference between destructive interference between Cooper pairs and this magnetic moment leads to so-called U-Shiba-Rusinov states, which are bound state appearing as the two peaks inside the superconducting gap. So this is superconducting gap of niobium diselenide, and in the vicinity you have two peaks, and these two peaks, which appear symmetrically with respect to the Fermi energy, they reflect one bound state, which is spin polarized state. Okay, so you have one peak which corresponds to the polarization spin down of excitations, and one which corresponds to spin up. And if you follow this peak as a function of position, you get very nice interference pattern, six-fold interference pattern, which corresponds to reflects the Fermi surface of this material. But also you see some fringes, and these fringes scale as a 2K Fermi minus 1. And the long range here, as you see, is 10 nanometers. It was for the first time as this effect was observed. It is one of the longest scale of U-Shiba-Rusinov state that allows, if you put impurity closer each to other, you can braid them and work out. So here, what we did, it's another system. It's one monolayer of lead, and there is a cluster of cobalt beneath this, and you get again a very sharp band of Shiba state, and these states, this bound state, as I told you, correspond to two peaks in the quasiparticle excitation spectrum. And now, if you go from the center of this island and you go away, what you see that these peaks they shrink to one peak, they merge to one peak at the Fermi level, then change again and change again if you go away. And this is this state at 0 has characteristic of Majorana statistics, and if you look how it looks in space, you get just a very nice ring. And this is a recently submitted paper. And one paper that could be interesting also for people doing superconductivity, it is a demonstration of so-called Anderson limit in superconductivity, when the size of superconductor becomes so small that the mean interlayer spacing, level spacing of electronic states become compatible to the gap that could be in this material, the superconductivity vanishes. This was a conjecture of P.W. Anderson, and we experimentally realized it. We deposited small nanocrystals of lead on the surface of indium arsenide, and with this situation, there is a band depletion due to presence of lead. So lead electronically is floating above indium arsenide. So when you put it a tunneling tip, you have a double tunneling junction, and you can charge your small islands with electrons. When you when you charge, so each time you charge, you pay charging energy, and that gives you these peaks in the tunneling characteristics. But in addition, you pay so-called parity energy. If the number of electrons sitting in the island is odd, then putting one more electron is more easy than the number is even in putting one more electron. It's because the electrons are bound. And so the distance between two peaks is 2 times the charging energy plus minus 2 times delta. Okay? So for instance, you can see the distance here is smaller than the distance there. And the distance here is again bigger, and distance here is again smaller. So if you look at the distance, you immediately get information about delta, about the superconductivity inside. Okay? And we follow this superconductivity as a function delta measured directly from this charging by parity effect, and as a function of the size of the volume of the islands, because the nature allows us to have a very wide collection of different sizes. And then you clearly see that this asymmetry, this parity effect, vanishes at about 100 nanometer cube. And if you take just a simple model starting from Kf, because in lead there are 2 Fermi surfaces, you can easily see that interlevel spacing becomes about 1 milli-electron volt exactly at the same position. So you have concomitance of increasing of interlevel spacing with reducing the size and vanishing of the superconducting gap at the same edge. Okay, now I'm back to the outlook of my talk, because we are in the vortex conference, so I should speak about vortices. And precisely because this year is very specific, we have lost a giant in our field. And so I would like to remind our modest contribution to this physics in very recent years. So I will mainly, you know that we contributed also in Abrikosov physics, Abrikosov vortex physics in confined islands, but my talk will be mainly for the Josephson physics. So we will try to see if it is possible to observe, using an STM, observe Josephson vortices in real space. Okay. I would like also to attract your attention to the recent handbook on small superconductors, to which we contributed, and several of you here already contributed in this book, so it's good for students. This is the system I will speak about. So what you see is the STM image of the system, which consists of atomically flat terraces of silicon, okay, on which we deposit lead at room temperature. And this deposition is as following. So what you see in blue, coded in blue here, it's not naked silicon, it is just one atomic monolayer of lead, which is amorphous in this case. It is not superconducting, it is dense amorphous lead. It's metallic but not superconducting. And since we continue to deposit more atoms of lead above this monolayer, other atoms, they do not cover epitaxially the substrate, but they combine in islands. It is so-called Stransky-Krassanov scenario in surface physics. Okay, so you have very rich situation. To do this, we need ultra-high vacuum conditions, of course, and also an STM working at very low temperature. It is homemade machine, etc. So the result of this, depending on, so we first prepare, of course, clean surface of silicon. It is not silicon oxide, it is clean silicon. So this is atomically resolved images of silicon. And we deposit at room temperature atoms of lead with the amount we control with a resolution of about 0.1 monolayer. And then if you do so, depending on the average coverage, you have 3 phases, 3 patches in the phase diagram. At a low amount of atoms, you get insulating phases. Then you have some multi-phases where different phases coexist on the same sample. And then you can isolate different phases. One that you obtain immediately if you just deposit one monolayer, it is amorphous. But you can also have some crystalline phases. okay, that are reported here as alpha square root 3 by square root 3, square root 7 by square root 3, etc., which correspond to the unit cell. These numbers correspond to the size of the unit cell in x and y direction with respect to the unit cell of silicon, underlying silicon. Okay. If you continue as you to deposit, as I showed you before, you get 3D growth, and this 3D growth gives you these islands. These islands are superconducting, so if now I take a collection of islands, I put a magnetic field. First, without magnetic field, I can do a tunneling spectroscopy. So here the color corresponds to the existence or not of the superconducting gap. So black color is a superconducting gap. You see immediately that all islands are superconducting. You see also that this wetting layer of amorphous lead is not superconducting. And then if you raise the magnetic field, you see abricose vortices entering into the sample, produce abricose of clusters or chains, and you can even go to the HC3 regime of superconductivity, where only the superconductivity at edges exist. If you study small islands, very small islands of the size of few psi, you can get a situation in which the confinement leads to giant vortices. So this is one abricose vortex, this is double abricose vortex, this is triple abricose vortex, which have different profiles because the cores have different spatial dependence depending on the winding factor. Now the question is, why there? We know that this amorphous monolayer is not superconducting. However, more dense, square root 7 by square root 3, and so-called striped incommensurate structure. One square root 7 by square root 3 corresponds to 1.2 monolayers of lead per monolayer of silicon. It means that we have more atoms on the surface on one monolayer, in more atoms of lead than atoms of silicon on the same surface. Okay, so it's very dense structure. Here, the interatomic distance lead is shorter than in bulk lead, so it's a sort of pressure. Okay. And also there is another one which is called striped incommensurate lead. It's a different crystallographic structure, but also very dense, still denser. And in 2010, this group, Chinese group, found a gap to appear in these two compounds below 2 Kelvin. Below 2 Kelvin in this and below 1.6 Kelvin in that. And they claimed that it is superconducting, okay? And we wanted to check it. And indeed, we repeated these experiments, and we observed a gap, which very clearly similar to what BCS predicts. And this gap is very interesting because on atomic scale, as here, you see the small balls here are individual atoms, and what you see here and here are the same, the gap maps, so it's a density of state of the same area. On the left side, you see the depth of the superconducting gap. So this is typically the density of states at zero energy. You see that the gap exists everywhere. It is blue, etc. And here is the nothing more but the height of the quasi-particle peaks. And so what you see immediately that while the gap is quite constant everywhere, the height of the quasi-particle peaks vary very rapidly on atomic scale. And this is something unusual for the superconductivity, in which, as all of you know, we do not expect variation of the order parameter or scales shorter than psi, which in this case, psi, I will show you, demonstrate to you, is about this size. Okay? In a little bit less dense square root 7 by square root 3 situation is even worse. You get not only very strong dumping of the quasi-particle peaks, but you also have a filling of the gap. Okay, and this is something really unusual in classical conventional superconductivity. So that we ask the question if it is really superconducting or something else, because the existence of a gap is not a proof of superconductivity. So we put a magnetic field. Yes, and this is a case of this striped incommensurate material, which is very dense. You see here individual atomic steps of this material, and they are reported here. Then you put a magnetic field, you see one vortex, and then you raise the magnetic field, you see several vortices. Some of them are pinned on the steps, but nothing specific. You can see this situation even in thicker films. Okay, so this material is certainly coherent superconducting state because you have vortices, which is a proof of the phase coherence. Okay, and the steps do not play any significant role. However, if you go to square root 7 by square root 3, the situation is very different. So here you have terraces. Okay, this is something like 1 micron by 1 micron image. Okay, these atomic terraces. Each part here is just one atomic layer more. Okay, then when you apply without magnetic field already, you see that the gap is suppressed in some locations, which are mainly on the step edges. And if you apply higher magnetic field, you see that the superconductivity is suppressed on the terraces and seems nothing happening inside. But then we understood that in fact these terraces these steps are intrinsic Josephson junctions, because the thickness of this superconductivity is just one atomic layer, and this is a disruption. So you have a Josephson junction, and then if you apply a magnetic field and you do some mathematical subtraction of your map at, for instance, here at 40 millitesla minus map at 0 field, you immediately see that there are vortices all sitting on steps. And these vortices, I will just explain in a few minutes, are intermediate Abrikosov-Josephson vortices. They are not purely Josephson vortices. It is intermediate case that Alex Gurevich predicted in '93. And once you saturated your steps by these intermediate Abrikosov-Josephson vortices, other vortices appear inside terraces, as you see here, and more clearly here. Okay, their number is perfectly what is expected for considering phi naught and the surface of this image. Okay, so a similar result was obtained by our Japanese competitors who observed similar situation in square root 7 by square root 3 indium, also monolayer, also on silicon, it's indium. And you have exactly the same situation. On steps, you have these elongated vortices, and on terraces, you have round vortices. And these elongated vortices is just due to the fact that you, while putting a vortex core, the singularity, just inside the junction, the system can accommodate a part of the phase gradient inside the junction, and so then it's more easy to accommodate the rest outside, okay, with respect to the round vortex core, as we know in Abrikosov case. So it seems a little bit disappointing because you can understand immediately that if you increase the importance of if you decrease the Josephson energy, allowing more and more of vortex perturbation to sit inside, you simply do not see anything by STM. While what we wanted to see is the Josephson vortex core, which supposedly could not exist. So what are the options? A standard Josephson junction, of course you need a Josephson junction for this. Our intrinsic junctions are not appropriate because they atomically, the width is just one atom, so we cannot go inside. And typically, if you take a standard SIS junction and you put numbers, in order to have a reasonable transparency, you need this width of about 1 nanometer. So if you use standard Josephson junctions, STM experiment is not possible. So there are two options, and we explored one of them. So the first one is to decrease the work function of insulator, for instance, using a low band gap semiconductor. For instance, if you put, instead of putting 4 electron volt as for vacuum, you put 40 millivolt, this extent for the same transparency could be 10 nanometers. And in such a case, you indeed 10 nanometers, quite a wide junction, you can go and probe. But for the moment being, we were not able to realize this. And there is another solution, is to use SNS junctions. And with SNS junctions, the Cooper pairs are decaying very rapidly in interfaces, and they are converted in Andreev quasiparticles and on both sides. And these Andreev quasiparticles decay on a larger scale. They decay on a larger scale, and this scale is related to the energy of quasiparticles, okay, and diffusion coefficient. So in principle, you can get, in some cases, in case we studied, we can get something like 10 nanometers in this, by this trick, and then you can study what happens inside. Okay, I want just to tell you one thing, because it's very important for recent discussion, that when you do a proximity effect, abusively, we always tell, okay, we induce superconductivity in the normal metal. And in these two papers, I will not stop, in these two papers, we show that if the metal, normal metal, is a superconducting material with low critical temperature, you can indeed induce a superconducting order in it by proximity with a stronger superconductor. So you will get really Cooper pairs. While if you use, why it freezes? If you use a superconductor, and here just a metal which doesn't have any attractive electron-phonon interaction, you will induce here quasiparticles, Andreev quasiparticles, but no superconductivity. So there is a clear difference, and it comes from the fact, I can show you the self-consistent equation in any theory, Bogolubov-Dejean or UZL, whatever, and it shows you that the superconducting order you induce in your proximity is always proportional to the V effective. Okay? So if a V effective is 0, you will introduce correlations, but delta will be exactly 0. Okay? So it is not because you have proximity effect that you have a superconducting. You always have superconducting correlations, but you don't have Cooper pairs. Okay. Now, of course, if you put two islands close each to other, you experimentally, by tunneling spectroscopy, you will see that this is the strength, the color is gives a strength of superconducting correlation. You clearly see that here there is a depletion due to this Andreev quasiparticles. If you do the same, this is a top view you see on the spectroscopy. So see blue, in blue it's a superconducting gap of lead on each island, left and right. And here you see the depletion in the tunneling characteristic due to Andreev quasiparticles. So we use this characteristic, which is depletion in the spectrum, to probe Josephson vortices inside. So how we do? For instance, here between two islands, you clearly see here that you have this Andreev gap here. Okay. Now, if you apply this gap is much smaller. This gap is much smaller than the superconducting gap in both electrodes, because it is not a superconducting gap, it's just a proximity gap. Okay, depletion. Now, if you apply the magnetic field, you can destroy superconductivity in one location, and this is nothing more but the core of the Josephson vortex. Okay, I can convince you also, if you go to these junctions, there are 3 of them. Okay, if I apply a magnetic field on 120 millitesla, I will have one vortex here. Okay, in this position. If I apply a field of 180 millitesla, I recover a proximity link here, and I will have 2 cores there. Okay, and the same situation appears here. And no vortex exists here, because here the junction is too short, and you cannot fit one Josephson vortex core inside. Okay, so the physics of the effect is very simple. In these islands, when you apply the magnetic field, you have a Meissner currents which circulate in opposite directions in 2 edges, because they circulate in all islands in the same direction. So in here, and you have for these currents you have phase gradients, and necessarily you will face such a situation in which you create a singularity of phase, and you get a destructive interference inside. We have a full consistent calculations of this, starting from Ginzburg-Landau model and extending this model inside, and with no free parameter we get complete agreement with the experimental data. So this is the end of my story. I would like just to promote a new device that you can produce. You can generate Josephson fluxoids without magnetic field. You don't need magnetic field to do this. Now, to our point of view, the currents are sufficient. Thank you very much.